Good morning. This is the video for AP Calculus section 4.5. And as you can see now, we're going to talk about integration by u-substitution. And what this will enable us to do is to undo some of the trickier derivatives. So far, all the integrals we know, all the antiderivatives we're able to take are just kind of our basic derivatives undone. Either the power rule or the natural log or the e to the x or the trig derivatives undone. It turns out that chain rule derivatives, we have to use what I'm calling here u-substitution to rewrite it in such a way that we can use kind of the only rules we know. So we're not using new integration rules. We're rewriting other functions in such a way that we can use the rules that we know. Let's look at two examples. The one on the left is very simple. It says the integral of x to the fourth dx is x to the fifth over 5 plus c. I know you all know that. But the thing, let's look on the left still. In yellow, I have the x. And of course, the derivative of x is just 1. So I put that little yellow 1 in there. But what's important, or I want you to notice that the derivative of that thing in yellow is kind of there. It's just times 1. And of course, you've already known that the integral of x to the fourth is in fact x to the fifth over 5 plus c. Let's compare that to this one on the right. My goal is to convince you that this one on the right is very similar. Instead of just x to the fourth, I've got a function of x to the fourth, happens to be x squared plus 7. But notice that the derivative of x squared plus 7, which happens to be 2x, is there also. I've circled it in yellow. And because that's true, or if that happens to be true, notice how similar these two integrals are. This one on the right is the whole thing in yellow, x squared plus 7 to the fifth over 5 plus c. It looks very similar to the one on the left. And what I want you to notice here is that if I were to not be sure, if I were to take the derivative, remember you can always check an integral by taking the derivative. If I took the derivative of this function to see if I'm right, well, I'd move the 5 out front, which would cancel with the 5 on the bottom. So I'd have x squared plus 7 to the fourth. And then the chain rule times the derivative of what's inside, the derivative of x squared would be 2x. So it does in fact work. So what I want you to notice is if you have a function, in this case raised to a power, the important thing here is that the derivative of x squared plus 7 is also part of the problem. That's what you're hoping for with these chain rule derivatives that you're undoing. Won't always be the case, but it'll start out being the case. So the good news is you don't have to just look at it like I did there and recognize, oh, since that x squared plus 7's derivative is there, the antiderivative of something to the fourth is something to the fifth over 5 plus c. We're going to actually add a step like right in the middle here to clarify or to be real clear on what part of the function are we going to circle in yellow, and is the derivative really there? So we're using this thing called u-substitution, where we are going to rewrite the function in terms of u, and then we are going to then take the antiderivative. So let's do this same one, which says x squared plus 7 to the fourth times 2x dx. Okay, here it is again. So we're going to use u-substitution, and the next slide kind of writes out what these steps are. But we're going to put this in terms of u. We're going to pick part of the function to call u. So we're going to say let u equal. Now, what you'll learn here quickly is the skill is which part of this function, which part of this problem should I call u? Should I call u x squared plus 7? Should I call u 2x? Should I call u x squared plus 7 to the fourth? Like, you've got options, and as these get more complicated, it might at first look like, I wonder what I should call u. But what I'm telling you is you want to pick a part of the function whose derivative is also there somewhere. And again, that won't always work, but at first it will. So in this case, since we already did this problem, you should by now realize that the derivative of x squared plus 7 is also in the problem. It's just 2x. So that's why I'm going to let u equal x squared plus 7. Now we're going to, again, now keep up here. We're going to take the derivative of this, still down here in blue. So I'm going to write 2 lines here, although I'm going to skip the first of the 2 after this first problem. Well, what's the derivative of u? Let's take the derivative of that thing we just called u. Of course, that's just 2x. That's du dx. Now, we're going to do a little bit of algebra here. We haven't talked about this yet, but it is, in fact, legal. We're going to multiply that dx to the other side of the problem. So I'm actually going to, instead of writing it like du dx equals 2x, I'm going to write it as du equals 2x dx. All I do is move the dx over. And again, as I said, after you do this the first time, I'm not going to write that line. I'm just going to go right to du equals 2x dx. Now, I want to rewrite the entire original problem in terms of u. I want to make a u substitution. So here's how I do this. I would literally still, this is still how I do this type of problem. I'm going to take everything up above in red, and I'm going to just real quick scribble near it what it's going to turn into. So for instance, let me change the color to green here. This x squared plus 7, that's what I called u, right? So that's going to say equals u. And this 2x dx, you'll notice from down here, that is literally just going to be du. I am substituting, I am rewriting the problem in terms of u. So what is this? I'll keep going in green here. So I'm going to rewrite this integral as the integral of, instead of x squared plus 7 to the 4th, it is now u to the 4th. And then instead of times 2x dx, that all became du. Look what I've done there. I rewrote the function in terms of u. And if you do that correctly, you will end up with an antiderivative that you know how to take. I know how to take the integral of u to the 4th du. It is, in fact, just u to the 5th over 5 plus c. That's a fairly simple power rule. I'm not finished, because in order to be finished, I have to go back to rewrite it in terms of my original variable, which was x. So it's very tempting to think we're done. But now where this thing says u, which I'm going to make bold and green here, we have to put that back. What did u equal? U was x squared plus 7. So this becomes x squared plus 7 to the 5th over 5 plus c. So there's as straightforward an example as there is of u substitution. We chose u, we picked which part of the function whose derivative is also there, and sometimes that's easier than others, and the more you practice it, the better you get at it. And then we take the derivative of u, and we then substitute. And this scribbling I did up here, as far as I would continue to do that, because otherwise I lose track of what parts are getting substituted for what. So I'm not just doing that as the first example to show you how to do it. I'm telling you that's how I do it to this day. So let's look at a few more examples. And so the goal today is we just do a couple examples where it's pretty straightforward u substitution. And then we're going to, I think, look at one where something goes wrong, something minor goes wrong, we have to worry about how to fix. So here's the process. It says using u substitution. It says choose u carefully. Again, ideally, you want to pick a part of the problem whose derivative is also there. That's the main key. And we'll see some other examples where there's some other either strategies or advice on what to choose for you. But for now, let's stick with that. And then we're going to rewrite the entire problem in terms of u. We're going to integrate, and we're going to rewrite the answer back in terms of x. So let's look at just a few examples here. So let's look at this one. All right. So I've got integral of 3 over 3x plus 1 to the 4th dx. So again, do I have a part of the function whose derivative is also there? I think I do. And I'm hoping you already see it, that the part of the function 3x plus 1, the derivative of 3x plus 1 would just be 3, and that 3 is conveniently right there. So this is going to be, we're going to let u equal 3x plus 1. And now again, I'm going to, instead of writing du dx, I'm going to erase this in a minute. Instead of writing du dx equals 3, I'm going to write that moving the dx to the other side. So I'm going to write this as du equals 3 dx. So as promised, I'm going to erase that. And now as I've said, I'm going to start circling and labeling stuff. So this 3x plus 1, the thing in parentheses there, that's just what I called u. And kind of everything else, this 3 dx, I now can rewrite this as du. So this becomes the integral of, I can either write it as du over u to the fourth. Make sure I did, that's a poorly drawn u there. That's not happening. There we go. I think I wrote that correctly. Now, if you'd rather write this, this is the integral of 1 over u to the fourth du. Those are absolutely interchangeable, and I don't care which of those you prefer. Those two are interchangeable. But now, again, if you choose u correctly and rewrite it in terms of u properly, it will be an antiderivative you know how to take. That would have showed up in section 4.1, basic antiderivatives. I could rewrite this as the integral of u to the negative fourth du. And I know that you know that the antiderivative of u to the negative fourth is, let's see, I'm raising the exponent by 1. So that's u to the negative 3 over negative 3 plus c. And now I might write that as, first of all, let's clean up the exponent stuff. This is maybe negative 1 over u cubed plus c. Make sure I did that correctly. Nope, I lost a 3. Negative 1 over 3 u cubed plus 3. That just moved the u to the negative third to the bottom. And then I can't stop there. I have to go back and substitute. I have to replace u with whatever u is. Grammatically, it sounds awful. And what I call u. U was 3x plus 1. So my final answer here is negative 1 over 3 times what I say u was, 3x plus 1 to the third, and then plus c. There's my final answer. So choosing u properly, and then taking the derivative of u and rewriting the whole problem in terms of u should, if done correctly, turn into an antiderivative that you will know how to take. All right, I do a couple more examples. What about this one? 5e to the 5x dx. Well, remember, we know that the integral of e to the x dx is just itself. Like, we know that. The problem here, of course, is the 5, but I want you to see it's not much of a problem. So, is part of the function's derivative here? Sure, the derivative of 5x is just 5. So let's let u equal 5x. The derivative of that is just 5 dx. So now, here I go again. This part right here, that I called u. And then this thing, which I'm going to weirdly circle, that 5 dx, I call du. So what does this turn into? It turns into the integral of, notice the blue e there, that didn't get substituted. That's still here, the e to the, let's see, instead of the 5x, e to the u, and then it's just the whole rest of this 5 dx is just du. It turns into the integral of e to the u du. That's itself. We like that. So the answer is just e to the u plus c. But we can't stop there. We have to put it back in terms of x. So this becomes, what's that? E to the, what was u? U was 5x. E to the 5x plus c. So again, I keep saying it, we're turning integrals that we don't know how to do by making a proper u substitution. We're turning them into integrals we do know how to do. All right, I think I've got two more. I've got one trig one, I think. Oh, not there. Let's do this one first, and we'll go back to the other one. So let's do a trig one. Integral of x times the sine of x squared dx. Now, let's talk about making bad choices for u, which you'll do at first as you learn this. This is not right. I'm gonna start over in a second. But if you think, let u equal the sine of x squared, if you decide to do that, well, what's a derivative of the sine of x squared? That would be the cosine of x squared times the derivative of x squared, which is 2x. Like, it would look like that. And that derivative is not in my original problem. So the good news here, if you choose u poorly, you won't get to an answer that's wrong. You'll get to a spot where you'll realize, I don't know what to do next, and it'll dawn on you, oh, I must have chosen U poorly. So let's erase that because that was not the right decision for you. You know what? Let's. I'm going to change this problem just a little bit to make it a little easier, because we haven't gotten there yet. Let's go ahead and make this. Let's make this a 2x. This is still a very basic, it turns out, U substitution. So now we've decided that calling U the sine of x squared I don't like. But as you now see, that the derivative of x squared is in fact 2x. So that should lead you, hopefully, to decide let U equal x squared. And so the derivative of x squared is 2x dx. Now let's make a substitution. So this thing in here is just, that's what I call U. And then this 2x dx, that whole thing there turned out to be du. So rewriting this, it becomes integral of, I still have the sine, but now instead of the sine of x squared, it's the sine of u. And then instead of 2x dx, it's just times du. And we know the antiderivative of the sine of u. That is what? Negative cosine u. Make sure I do the right, the derivative. Yeah, I have my negative sign correctly there. Plus c. And then again, my last step is to put it back in terms of x, and u, again, it's just a matter of replacing, you're replacing u with what u is, and u here is x squared. This is negative cosine of x squared plus c. Again, I could always take the derivative back to check it. If I started here and took the derivative, I know that you will know the derivative of the negative cosine of something is, in fact, the sine of it. So it would be the sine of x squared. And then times, chain rule, the derivative of the inside, the derivative of x squared is 2x. That would get us back where we started. Okay, so last thing is, what if it doesn't match exactly? You pick u correctly, you start substituting in terms of u, but not every part of the problem substitutes cleanly. This last example shows that. I think it looks like this one. Yeah, so let's look at this. Let's look at this one. So remember, there's still no product rule for antiderivatives, so we can't do that. So we have to, if you're not sure what to do with an integral, think U substitution. So now the question, as usual, becomes what should I call U? And as I said, we want to call U part of the problem whose derivative is also there. And it doesn't quite work here. I see this, and I'm going to circle it here. I see this. If I were to call that u, which does turn out to be the right decision, if I did that, it would end up as the integral of u squared. I like that. That would be u to the third over 3. So I like where that would take me. But the derivative of x squared plus 1 is 2x. I have that x out front. I don't have a 2. So what I want you to notice is at the moment, the only problem is the constant. The constant that we wished was there isn't there. And this example is to show you that that's fixable. So let's still call u x squared plus 1. And that makes the derivative of x squared plus 1 is 2x dx. Now, as I normally at this point, I would start substituting. This thing that I already squared up here, that's still u. But you'll notice what I have here left to get rid of might be the wrong word, is this x dx. But down here it says 2x dx. I wanted to say x dx. We may have to do a little bit of algebra to make this equation at the bottom, make it match better. And it currently down here, it says 2x dx, but up above, I noticed that I wanted to say x dx. Let's just divide by 2. Let's call this 1/2 du equals x dx. Like I did the algebra necessary so that it does match. Now that thing that I circled in that weird shape which says x dx, I'm now saying this I'm going to substitute to become 1/2 du. So the constant was wrong, but I was able to fix it. Now let me get rid of this arrow so I can rewrite the integral up here. So now let's be careful with what this becomes. This becomes the integral. I still have, instead of x squared plus 1 squared, I have u squared. But now what's left? What was left was the x dx, which we now said was 1/2 du. I'm going to, cheat's the wrong word. I'm going to use a shortcut. I'm going to erase this moment also. Instead of putting times 1/2 du, which would be right, I'm going to already know that the constant, I'm just going to move that out front in front of the integral sign because I'm allowed to do that with a constant. So instead of writing that times 1/2 du, whenever I have a constant there, I'm going to put the 1/2 out here and then the du out there. So I rewrote the original function in terms of u. I still had to choose u wisely. Now I think I can run with this from here. This becomes, let's see, this is now an antiderivative we know how to do. This would be 1/2 u to the third over 3 plus c. All I did was use the power rule there. I'll continue this over here. This becomes u to the third, what is that, over 6 plus c. And then please, 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 please don't stop there. Rewrite it in terms of x. And what did we call u? U was x squared plus 1. So my final answer is x squared plus 1 to the third over 6 plus c. So there is your introduction to u substitution. And so far, one of two things is going to happen. Either it will be set up perfectly where the derivative of u is right there like you want it to be, or like this last example, the only issue might be a constant. And we saw in this example how to deal with that. So there are other things that show up. We have to learn how to deal with that. Will be the next one. So that is it. Your assignment is there. I guess just, I don't know, maybe 10 or 12 problems. It's only on one, so you can check your work in the back of the book. Again, as always, if you have any questions, reach out. So have a great Tuesday.